electric field lines. Electric field lines are only a way of representing electric field, which means that they are imaginary lines and they are not the electric field itself. We only use them to represent the electric field. You can represent electric fields with electric field lines. An electric field line indicates the direction of the force due to the electric field on a positive tested charge. As we did before, we said to find the direction of the electric field, you have to find the direction of the electric force acting on a positive charge. They should be in the same direction. The direction of the electric field at any point is the tangent drawn to a field line at that point. We will see this on a figure. And the spacing between the field lines indicates the electric field strength. So the smaller the distance between the electric field lines, it means that the electric field will be stronger. If the distance increases, then the electric field is becoming weaker. When more than one electric charge is present, the electric fields add together. Let's see. Two like charges, the electric fields diverge away or bend away from each other. This is the tangent line, this is the direction of the electric field when you draw it at a point. If you look next to the charge, you will see that the distance, for example, the two lines I'm pointing at, as they go away from the charge, the distance between them increases. So at this point, the electric field is stronger. As you go away, it becomes weaker. And for both the charges, the electric field lines are pointing outwards. Now, if we have one negative on each side, one negative charge on each side, so both charges are negative, the electric field lines point towards the charge, and the electric field direction is a tangent to the electric field line at that point, and they converge in. For positive and negative charges, unlike charges, the electric fields add up. As you see, they connect between them, and also the electric field line goes this way. For example, at this point, it should be going this way. The number of electric field lines is proportional to the strength or the magnitude of the electric field. So as we said, if we have a charge that has more electric field lines than another charge, then it has a stronger electric field. So the stronger the field is, means more electric field lines will be there. The relation between the magnitude of the charges and the number of electric field lines can be found using this formula. Q1 over Q2 is equal to N1 over N2. Let's apply this formula to see how to solve. We have this system. For the figure shown, describe the polarity for each charge. Find the ratio of Q1 to Q2, and if the magnitude of Q1 is 4 millicoulombs, find the charge on Q2. Okay. First of all, the polarity of the charge. As you see, the electric field line is diverging out, or it's pointing away from both charges. This indicates that they are both positive, because for a positive charge, the electric field diverges out. Part B, find the ratio of Q1 to Q2. So, Q1 over Q2 is equal to N1 over N2. If we count the number of electric field lines, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So N1 is 12. Now N2, 1, 2, 3, 4, 5, 6. We have 6. So 12 over 6, which is 2 over 1. Then Q1 to Q2 is 2 to 1. This is how we write the ratio. Part C, if the magnitude of the charge on Q1 was 4 millicoulombs, find the charge on Q2. Q1 over Q2 equals N1 over N2 again. N1 is 12, N2 is 6. Q1 it's given in part C, 4 millicoulombs. So only Q2 is an unknown. We replace to find the answer. So 4 over Q2 equals 12 over 6. Then Q2 is 2 millicoulombs, and I took it out of the absolute value because we know that it is positive. Now, this exercise, the same exact exercise, but with a different figure. Now, as you see, the lines are pointing towards Q1. They are converging in. Same thing for Q2. They are converging in. Then both charges are negative. Now, the ratio, we use the formula Q1 over Q2 equals N1 over N2, and we replace Q1 is 12 lines if you count them, and Q2 we have 2, 5, 8 lines, so 12 over 8 or 3 over 2, then Q1 to Q2 is 3 to 2. For part C, we will use the same formula. Q1 is given as 6 microcoulombs. We replace to find the answer. So Q1 over Q2 equals N1 over N2. Then 6 over Q2 equals 12 over 8. Then you calculate Q2 and it is negative 4 microcoulombs. So when I took it out of the absolute value, I get 4 microcoulombs. But since Q2 is with a negative polarity, as we mentioned in part A, then I have to write that it's negative. For this system, from the shape of the electric field lines, we conclude that we have two unlike charges, since the electric field lines added up between both charges. For part A, describe the polarity of each charge. If you take a look at Q1, you will see that the electric field lines are diverging out of Q1. They are pointing away from Q1, so Q1 is positive. For Q2, the lines are going into or converging towards Q2, so Q2 is negative. Part B, we follow the same order. Q1 over Q2 equals N1 over N2. Let's count the number of electric field lines for each. I will start from this one for Q1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for Q1 I have 10. For Q2, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so N1 is 10 and N2 is 8. Note that the electric field lines between them, I'm talking about those, the ones that are common between them, they count for both. So Q1 over Q2 equals N1 over N2, which is 10 over 8, which is 5 to 4. So the ratio will be Q1 to Q2 is 5 to 4. Part C. If the magnitude on Q1 was 4 nanocoulombs, find the charge on Q2. We will use the same formula, Q1 over Q2 equals N1 over N2. We replace the values given, and we find the answer for Q2 as 3.2 nanocoulombs, but since the electric field lines converge, and then it is negative 3.2 nanocoulombs.